Hello everyone, welcome back. So in this video we are going to learn about stability concept. Okay, so we are going to learn about stability. So what is stability and how many types of stability are there and how to find the different types of stability of a given system. Okay, so if you are first time to my channel, please consider subscribing. Stability. So stability is a concept which is applicable only for LTI systems. Okay, so it is applicable for LTI systems. So an LTI system is said to be stable if it satisfies the following conditions. If it satisfies the following conditions. So the first condition is if the input is 0. So if the input is not given for any given system, then the corresponding output should also be 0. Okay, so if the input is 0, then the output should also be 0. And second, if the input is bounded, so if a bounded input is given to a system, then it should produce a bounded output. Okay, so irrespective of all initial conditions, okay, such type of system is said to be a stable system. Okay, so any system is said to be stable if an LTI system is said to be stable if 0 input results in 0 output and bounded input results in bounded output. Okay, so what are bounded inputs and what are bounded outputs we'll discuss later. Okay, so in the concept of time response we'll discuss that. Okay, what are the bounded inputs which we have to give. Okay, so this is the definition of stability. Then how many types of stability are there? Types of stability or classification of stability. Okay, so different systems are classified into how many types? So there are three types of stability. 3 types of stability we can comment on a given system. Okay, 3 types of stability for a given system. One is stability, other is stable system. Okay, second is marginally stable system, and third is unstable. Okay, stable, marginally stable and unstable. And in stable there are again 2 types: absolutely stable system, and second type is conditionally stable system. Okay, so these are the classifications of different types of stability of a given system. Okay, so first of all, stable system. So when can we say that a system is said to be a stable? So closed loop poles of the system, if the closed loop poles of the system lies in left half of S-plane, then that type of system is said to be a stable system. Okay, so then that type of system is said to be a stable system. So again I have told you there are 2 types of stable systems. One is absolutely stable system. So any system whose if the system stability, so if the system stability is, if the system stability is defined for all the range of system parameters, then that type of system is said to be absolutely stable system. Suppose example s cube plus 9s square plus 6s plus 24 is equal to 0. So this is said to be a stable system. This is your characteristic equation. Okay, if this is your characteristic equation, from this we'll get the closed loop poles, and this system is said to be a stable system. Okay, don't worry, I will tell you how to find the stability of such type of systems, okay, in the upcoming concepts. And some of the systems are said to be conditionally stable systems. If the system is stable for only certain range of system parameters, only for certain range of system parameters, if the system is stable, then it is said to be a conditionally stable systems. So generally characteristic equation of such type of systems involves one constant, like s cube plus 9s square plus 6s plus k is equal to 0. Now it depends on k. Okay, so now it depends on the k value, that is, it depends on k value. So only for certain ranges of k only, the system is said to be stable. Okay, so even though it is stable, but it is only stable for only certain range of values of k. Okay, so such type of system is said to be a conditionally stable system. Okay, so for this system we'll get 0 less than k less than 54. Okay, so for only these ranges of k, the system is said to be stable, and outside this range the system is said to be either other two, either marginally stable or unstable system. Okay, you may get anything. So that is why only for this range of system parameters the system is said to be conditionally stable. Okay, so that is why it is said to be conditionally stable system. Okay, so now it depends on k value. Okay, so as we discussed, for the stability, for a stable system, the poles must lie in left half of s-plane, Okay, so if the poles lies in the left half of s-plane, so if you draw an s-plane here, so real part of s is sigma and imaginary part is j omega, and if you have a pole like this on the left half of s-plane, like minus a, then the transfer function is given by, its transfer function is 1 by s plus a, so that you will get s plus a is equal to 0 and s is equal to minus a. So we'll get a pole at s is equal to minus a, which lies in the left half of s plane, and its corresponding time domain equation is e power minus at into u of t. So as t tends to infinity, this output is tending to 0, so this output becomes 0. That means even at t is equal to infinity, its value is a finite value, so we can say that it is a stable system. As t tends to infinity, if its value is so we'll discuss that later. As t tends to infinity, it is giving a 0 value, so it is said to be a stable system. Second type of stability is marginally stable system. Okay, so for marginally stable system, poles lies on imaginary axis. Which are non-repeated. Okay, so poles lies on the imaginary axis. So if the poles lies on the imaginary axis, then how will be the s-plane? Like this, complex conjugate poles. If they exist in the imaginary planes, always will get a complex conjugate pole. So suppose j1 and minus j1. Okay, so j1 and minus j1, if you have, okay, so this is j omega and this is minus j omega. So what will be the transfer function then? Transfer function is equal to 1 by s square plus 1. So then only s square plus 1 is equal to 0, s square is equal to minus 1, s is equal to plus or minus j1. Okay, plus j1 and minus j1. So such type of system, when you have the output, so if you have impulse response, so if transfer function is given, so what will be its corresponding impulse response? It will be sine t. Okay, it will be sine t into u of t, right? So when you draw sine t, so that means when you draw the output impulse response c of t, then how will be the output? So the output will be like this. So it will be sine t. Okay, so if you draw the output for this exponential decrease, so for the stable system, how will be the output? So at 0 its value is 1, and it decreases exponentially like this, and finally becomes 0. Okay, so this is said to be a stable system output, and this is said to be a marginally stable system output. Okay, a marginally stable system output. So for marginally stable, poles lies on the imaginary axis like this. Okay, and system output is, so if the system output is, the amplitude is constant, yes or no? Amplitude is constant and frequency is also constant, and it is sinusoidal in nature. System output is constant amplitude and frequency. Constant amplitude and constant frequency. Constant amplitude and frequency of oscillations. Okay, or it is also called sustained oscillations. Okay, so that is what the marginally stable system represents. Okay, so the third type of system or third type of stability is unstable systems. So there are some types of systems which are unstable in nature. So how can we find whether the given system is unstable or not? Is poles, same closed loop poles, lies in right half of S plane. Okay, so system output is exponentially increasing. Okay, if they are real in nature. If they are complex in nature, system output is exponentially increasing sinusoidal signal, sinusoidal oscillations. Okay, so I'll make a separate video on this different types of system output depending on the pole's location. Okay, so as of now, just remember that system output is exponentially increasing. When it is exponentially increasing, I'll show you. So the poles will lies on the right half of S plane. I'll take only this case. This case I'll explain in the next video, which I will take for different types of poles, what will be the output looks like. Okay, so this is j omega and this is minus j omega. This is sigma, the real part, and this is minus sigma. So such type of signals where the poles lies in the right half of S plane, then such type of signals is said to be unstable signals. So for this transfer function is 1 by S minus 1. Okay, so if you take it as 1, so 1 by S minus 1, so that S minus 1 is equal to 0, S is equal to 1. Okay, so for that what will be the impulse response? Impulse response is C of t is equal to e power t into u of t. E power t into u of t. So when you draw this, e power t into u of t is an exponentially rising signal. So when t is equal to infinity, C of t is equal to e power infinity. E power infinity is infinity. That means it is not bounded. So output is not bounded even at t is equal to infinity. So for input is bounded, and output is not bounded. Okay, so output is not bounded, then that type of system is said to be unstable system. Okay, so if input is bounded and output is also bounded, then it is called as stable system. Okay, so marginally stable is about to become unstable. It is verge on instability. Okay, it is on the verge of instability. Okay, it is about to become unstable. So if it value changes, then it becomes unstable. Okay, so pole location, you just shifted towards right, it becomes unstable. Okay, such type of system is said to be marginally stable, or it is also called critically stable system or limitedly stable system. We can call marginally stable system, okay, as a critically stable system or limitedly stable system. Okay, so this is how we can classify different types of stability based on the pole location. In the next video, we will see different types of stability, that is all the three types of stability and their different cases also. Okay, so we'll take the different cases also and discuss with perfection how the output looks like for a given type of pole location. Okay.